Hi, welcome to this webinar. The title of this webinar is Introducing ICRP Publication 145, Adult Mesh Type Reference Computational Phantoms. First, thank you all for attending this webinar. I'm Chanyeong Kim from Han University in Seoul, Korea. I'm the moderator of this webinar. I'm a member of ICRP Committee 2, which is responsible for computational human phantoms, biokinetic models, and dose coefficient calculations. I'm also serving as the chair of ICRP Task Group 103, which is developing mesh-type reference computational phantoms, which we will discuss today. Today in this webinar, we will have 3 presentations. First, I will make about 20-minute presentation to explain the limitations of voxel-type reference computational phantoms and the phantom geometry in general. And then the next speaker will explain ICRP Publication 145 and adult mesh type reference computational phantoms. And the last speaker will explain how to download and use the phantoms with some demonstrations. Then we will have a Q&A time for about 30 minutes. Okay, with that, I think we can start. So I will do my presentation first. Hi, I'm Chanyeong Kim, and the title of my presentation is Introduction to Mesh-Type Reference Computational Phantoms. In this presentation, first I will explain the limitations of the current voxel-type reference computational phantoms, and then I will spend some time to explain the phantom geometry, that is tetrahedron mesh geometry, which is used for new mesh type reference computational phantoms. Before I start my presentation on computational human phantoms, first let me briefly explain the voxel geometry. What is voxel or voxel geometry? Well, the word voxel is contraction of volume and pixel. In two-dimensional space, we have pixels. And likewise, in three-dimensional space, we have voxels. We can use these voxels to construct models like these car models. If you use small voxels, then we can construct a detailed model like this. But if you use large voxels, then we can construct only a very rough model like this. Even though the voxel geometry has been the geometry of choice for computational human phantoms for more than 30 years by now, the voxel geometry has a limitation. First, it is very difficult to construct a model with very thin layers or smaller structures. For example, to define a thin layer in a voxel model, the size of the voxels should be very small. That is, it should be much smaller than the thickness of the layer, which is quite often not practical, especially for human bodies, in which the thickness of the radiosensitive target layers and source layers are very thin. That is a few microns or tens of microns. And we cannot use the voxel geometry to define these thin layers. Also, the voxel geometry is not deformable, which means we can only develop a rigid model using the voxel geometry. The voxel geometry also shows jagged stair-step surfaces. Okay, with that, let me move on to computational human phantoms. This slide shows computational human phantoms, which are used in ICRP for dose coefficient calculations. The phantom in the left is called mathematical phantom or stylized phantom, mostly used in the past. And the phantoms in the right are voxel phantoms, which are constructed with voxels, which I just mentioned. In fact, these voxel phantoms are the current ICRP reference phantoms for adult male and female. And these phantoms were released in 2009 with ICRP publication 110. These phantoms were developed using the CT image data of real human bodies and realistically describe the organs and tissues of the human bodies when compared to the stylized phantom. Certainly, these voxel phantoms are an improvement over the previous stylized phantoms, but still, these phantoms have limitations due to the nature of voxel geometry. That is, in these phantoms, we can see jagged stair-step surfaces not fully closed. Thin or tiny structures cannot be represented. For example, the stem cell layers in the alimentary and respiratory tract organs cannot be defined. So for the ICRP, it was necessary to use 12 additional stylized phantoms for those coefficient calculations. Here are some examples of stair-step surfaces. This slide shows the skin of the ICRP publication 110 voxel type reference phantoms. And you can see that the stair-step surface, surface of the skin, which has a lot of holes. In addition, the 50 micron thick skin target layer cannot be defined. We also have similar problems in the hollow organs, there's wall organs, their stomach, urinary bladder, and gallbladder. Now it's about the respiratory tract organs. In case of respiratory tract organs, the target layer is very thin. For example, this slide shows the ET1 region, and the target layer of this region is the base layer, and the thickness is only 10 microns. But this thin layer is not defined in the current ICRP publication 110 reference phantoms, simply because in these phantoms, the organs and tissues are defined by large voxels. Therefore, an additional stylized phantom was used for self-calculations for weakly penetrating radiations. The situation is the same for ET2 region, large BB region, and small BB regions, and 3 additional stylized phantoms were used for self-calculations representing these tissues. We also have the same problem for the alimentary tract organs. In this case, 7 additional stylized phantoms were used for self-calculations for weakly penetrating radiations. This slide shows the eye models of the ICRP publication 110 male phantom. Here the red color indicates the lens of the eyes, and you can see here that the lens of the eyes are directly exposed to air, which is anatomically incorrect, resulting in significant overestimation in lens dose for weakly penetrating radiations. So the ICRP again used additional stylized phantom for lens dose calculation. This is the stylized phantom used by the ICRP for the lens dose calculations. So if I summarize here, the ICRP is not using only the ICRP reference phantoms for those coefficient calculations. And the ICRP is using at least 12 additional stylized phantoms for internal and external dose coefficient calculations, which is not only complicated and error-prone, but also provides less consistency in those coefficient calculations. There are some more limitations. First, the ICRP publication 110 reference phantoms were matched to reference organ masses exclusive blood content, not inclusive. So all organs are smaller than usual. that is by about 3 to 10%. And some neighboring neurons are not in contact, which can cause errors in self-calculations for low penetrating radiation, such as leptons and low-energy photons. And these phantoms are not formal. Okay, I'll skip here. So these limitations were discussed in ICRP Committee 2 meeting in Abu Dhabi in 2013, and the committee decided to convert the voxel-type reference computational phantoms into high-quality mesh format to overcome these limitations. And the general understanding and consensus was that the new phantoms will replace current voxel-type reference phantoms for the next set of general recommendations. For this project in ICRP Committee 2, we established a dedicated task group, that is Task 103 in 2016. And the objective of this task group is to produce next generation high-quality mesh type ICRP reference computational phantoms, which include continuous and fully enclosed surface for the skin, stomach, gallbladder, and urinary bladder, and also include the thin target layers in the alimentary and respiratory tract organs, and also in the skin. And finally, the developed phantoms will also include detailed and more accurate models for the skeletal system, eyes, lymphatic nodes, blood vessels, hands, and fists, and etc. This slide shows the initial members of the task group. Here we have Maria Janko and Nina Patushians, who developed and used adult voxel-type reference phantoms, which were published in ICRP publication 110. Also, we have Wesley Bolts and Chunshik Lee, who developed pediatric voxel-type reference phantoms. We also have Keith Ackerman, who developed stylus phantoms in the past and has a lot of experience in those coefficient calculations. So you can say we all work together. This slide shows the current status of our task group. The goal of our task group is to develop a full set of mesh-type reference computational phantoms, which include adult phantoms, pediatric phantoms, and pregnant female phantoms. For adult phantoms, the phantoms were completed, and report was published as ICRP Publication 145 in 2020. For pediatric phantoms, the phantoms were completed, and the report was also completed, and the public consultation was also completed, and the report will be published very soon, that is within a few months. Finally, for pregnant female phantoms, the phantoms are almost completed, and the self-values will be calculated very soon. And I think it'll take a few months. Then the report will be published in 2024. That is next year. Today, the next two speakers will explain ICRP Publication 145 and adult mesh-type reference computational phantoms in detail. But before we move on, let me spend some time to explain the phantom geometry in general. This is because the new mesh-type reference computational phantoms are developed in a new geometry type, not voxel geometry, which is called tetrahedron mesh. The tetrahedron mesh is classified as unstructured volume mesh, which is almost ideal for phantom geometry, but not very familiar to many people in computational human dosimetry. So I will spend some time to explain this geometry. As I mentioned earlier, the stylized phantoms were used in the past, but these days mostly we use phantoms in voxel geometry or nervous polygon mesh geometry. But these geometries have limitations. First, as I explained earlier, the voxel geometry is not deformable and suffers from stair-step surfaces, and it is very difficult to model very thin or very tiny tissue structures. On the other hand, the nervous polygon mesh geometry is deformable and smooth, but it cannot be directly used in Monte Carlo code. And that's nervous polygon mesh geometry should be voxelized before it is used in a Monte Carlo code. In other words, to be used in a Monte Carlo code, the nervous polygon mesh phantom should be first converted to a voxel phantom through the voxelization process. Then the voxel phantom is the one which is used in the Monte Carlo code for those calculations. So we can say that the nervous polygon mesh geometry is not fully free of the limitations of the voxel geometry. That is because the final geometry used in the Monte Carlo code is the voxel geometry, not nervous polygon mesh geometry. So for the new ICRP reference phantoms, we decide to use a different geometry type. That is a tetrahedral mesh geometry. Basically, we are filling the nervous polygon mesh model with many tetrahedrons using a process called tetrahedralization, which is very similar to the process of voxelization. But the difference is that the nervous polygon mesh model is now filled with the tetrahedrons, not voxels. Like this, the sphere is polygon mesh, and the sphere polygon mesh is filled with many small tetrahedrons, not voxels. Then the good news is that the resulting tetrahedral mesh geometry have the advantages of both voxel geometry and nervous polygon mesh geometry. The tetrahedral mesh geometry is still deformable and smooth, like the nervous polygon mesh geometry, but at the same time, the geometry can be directly used in Monte Carlo code without voxelization. That is keeping the original quality or fidelity of the mesh phantom. And the computation speed is also very fast. Also, if we use the tetrahedral mesh, we can even model the sub-organ density variation of an organ using the tetrahedrons which fill the organ model. It should be noted here that if you use the nervous polygon mesh geometry, which is a surface mesh geometry for boundary representation of the region of the organ, we cannot model the sub-organ density variation of the organ. And the organ should be assumed to be homogeneous, which is not always true and sometimes becomes a critical limitation. This slide again compares the voxel geometry, nervous polygon mesh geometry, and tetrahedral mesh geometry. First, the voxel geometry is classified as structured volume mesh. It is structured mesh, and it's volume mesh based on volumetric representation. Consider that in this geometry, an object or an organ is defined by many volumetric cells, that is voxels. This geometry has the advantages of fast simulation and the capability of sub-organ density variation modeling. The nervous polygon mesh, this one, is classified as unstructured unstructured surface mesh. It is unstructured mesh, and it is surface mesh based on boundary representation, considering that in this geometry, an organ is defined by a single closed surface, which defines the boundary of the organ. This geometry has the advantages of flexibility, allowing deformation and precision modeling. Finally, the tetrahedral mesh geometry, which is used for new mesh type reference computational phantoms, is classified as unstructured volume mesh. It is unstructured mesh and it is volume mesh based on volumetric representation, considering that in this geometry, an organ is defined by many volumetric cells, that is tetrahedrons. This geometry has the advantages of both voxel geometry and knobs polygon mesh geometry. That is, the geometry provides flexibility and precision modeling, which are the advantages of voxel, or the advantages of Norb's polygon mesh geometry, but also provides fast simulation and the capability of sub-organ density variation modeling, which are the advantages of voxel geometry. This is why we decided to use the tetrahedral mesh geometry for the new mesh type reference computational phantoms. Okay, that concludes my presentation. Thank you for your attention. Okay, now I think we'll move on. We'll move on to the next speaker, next presentation. Let me just. If you have any question at this point, please hold it until the Q&A time at the end of this session, or you can leave your questions in the Q&A window. The title of next presentation is Development of Adult Mesh Type Reference Computational Phantoms, which will be presented by Professor Yeonsu Yum. Professor Yum is a professor of Yonsei University, which is one of the best universities in Korea. He received his PhD degree in nuclear engineering from Hanyang University in Seoul, Korea in 2017. And then he did his postdoctoral research at Hanyang University for a very short time. And then he moved to the United States to join National Cancer Institute to work as a visiting fellow for about 3 years. Then finally came back to Korea to join Yonsei University as a professor. His main research area is computational human phantoms and dosimetry. In fact, his PhD thesis topic was to develop the adult mesh type reference computational phantoms, which he will present today. He wrote the most part of ICRP publication 145, so the report became his PhD thesis. So I can say he's the one who knows best about ICRP publication 145 and the adult mesh type reference computational phantoms. He's very active in research. He has published many papers, and that is, he published 72 journal papers. He is also serving ICRP as a member of task group for three task groups, including task group 103, which develops mesh type reference computational phantoms. Okay, with that, I think we can start. Yeonsu, if you're ready, please go ahead.
Okay, so thank you so much for the kind introduction, Professor Kim. Okay, so good morning, good afternoon, or good evening. I'm Yeonsu Yum from Yonsei University, and I'm also a member of ICRP Task Group 103. Personally, I'm so excited, and it is a great honor to present in the ICRP webinar today. So in the previous presentation, Professor Kim clearly explained why we have developed the mesh type reference computational phantoms. So in this presentation, I will explain how we developed adult mesh type reference phantoms with some discussion about the improvement and dosimetry impact against the voxel type reference phantoms. So phantom development procedure can be largely divided into the three parts. The first part is the conversion of the voxel type reference phantom into the mesh format. And the second part is the inclusion of blood in organs and tissues. And the third part is the inclusion of the micron scale target and source region, so in the organ such as skin and alimentary tract system, respiratory tract system, and the urinary bladder. Okay, so now I would like to give some more explanation on detail, the part one, the phantom conversion. So general shape of simple organs such as the liver, for example, is quite well represented in the voxel model, voxel phantoms. So these such simple shape organs and tissues actually, the most cases could be directly converted from the voxel phantoms, voxel model to the high quality, the mesh model following the conversion procedure. So first, the voxel model was converted to the primitive polygon mesh model by using the 3D Doctor program. However, the primitive mesh models were usually not high quality model. The surface is not smooth, and sometimes we found some defects such as small holes and also surface intersection faces. So we need to address this problem. So therefore, this primitive mesh model was carefully refined by using the rapid form program, the smooth outer surface, and minimize the number of the faces, and match to the reference organ mass. So this conversion method was successfully applied for most of the simple organs and tissues to make high quality mesh models. However, for Ragin testing, which is a relatively complex structure, we needed to additionally apply the nerves conversion process by using the Rhinoceros software. During the conversion process, to keep the original shape of the voxel model as much as possible, so we monitored two parameters that can mathematically indicate how two objects are geometrically similar. So the first parameter is called dice index, which can be calculated using this equation. This eventually indicates the volume of refraction between the voxel and mesh model. And we attempted to keep the dice index below 95% of the maximum achievable dice index during the conversion. And at the same time, the second parameter is the centroid distance between voxel and mesh model we monitor. So we attempt to keep the centroid distance below 0.5 millimeter during the conversion. This slide shows the internal organs and tissues in the mesh model, converted from the voxel model. As you can see, the converted mesh model look more realistic, especially the smooth surface, and also well maintain the original shape of the voxel models. And the skin in the mesh model was also well converted from the voxel model. This slide actually shows some improvement of the skin mesh model over the voxel model. As explained by Professor Kim, the skin model is not fully enclosed, and some internal organs such as muscle and breast are directly exposed to the air in the voxel phantom. So as you can see, this limitation is now fully addressed in the skin mesh model. In the skeletal system, we also converted the most of the bones to high quality mesh model by using the similar direct conversion method as explained before for simple organs. During the conversion, we found that the voxel model of the female sacrum has spongiosa only. Actually, this is anatomically incorrect. The spongiosa should have been enclosed by the cortical bone as like the male sacrum. Therefore, we borrow some cortical bone from the female lower leg bones to define the cortical bone for the female sacrum. In contrast to simple bones, we were not able to convert the spine voxel model to high quality mesh model. This is because the detailed structure of the spine is not precisely represented in the voxel phantom due to the limited voxel resolution. Actually, so we decided to give up the conversion method. Instead, we employed and adjusted existing the high quality mesh model of the spine to match the voxel model as similar as possible. The same approach was applied for the hands and the feet as well. So during the adjustment, we found that the female phantom shows toe standing feet shape. So we simply rotated the feet bone to be the normal standing posture. So this is the entire view of the skeletal system for the male phantom. This is for the female phantom. This slide also shows some improvement of the skeletal system in the mesh model. So as like in the voxel model, as like the skin, in the voxel model, the red part, which this is the spongiosa, which is not fully enclosed by the thin cortical bone because of the voxel resolution. So this anatomical limitation is also fully addressed in the mesh model, as you can see. Okay, so now I'm going to talk about the small intestine. The small intestine, we actually could not convert the voxel model to the high quality mesh model, reflecting the high complex passageway as like the realistic small intestine model. Actually, I think we believe no one can clearly distinguish the passageways in the small intestine voxel model. So we developed a new approach for small intestine modeling. The first, we created the frame that can fully include the small intestine voxel model. And then within this frame, we randomly generated a small intestine passage center line. For the random generation, a dedicated in-house program was developed following the algorithm as shown in the flowchart. And then we convert the center line to the pipe model by using the pipe and mesh functions in the Rhinoceros software. And then the generated pipe model was compared with the original voxel model by monitoring geometric similarity parameters such as the volume over reflection. So finally, we repeated this procedure 1,000 times to generate 1,000 different small intestine models. And then we selected the best model considering not only geometric similarity, but also dosimetric similarity with the original voxel model. This is the small intestine model for the male phantom. And this is the female phantom small intensity model. So as you can see, the mesh model will represent the realistic the passage of wave, and at the same time, it is quite similar with the general shape of the voxel model. So lymph node, these are the lymph node model of the voxel phantom. But we could not this voxel model convert to the high quality mesh model due to the complexity and distributed nature in the body. So we newly model the lymph node following the procedure that was actually used for the construction of the ICRP pediatric voxel phantoms. We use the reference mass of the lymph node adopted in ICRP publication 133, and we derive the site-specific the number of the lymph node as well as the mass. Based on this data, we randomly generated the lymph node in the mesh phantom following the algorithm shown in the flow chart. So this slide shows the lymph node distributed in the mesh phantom. As explained by Professor Kim, the range of the eye in the voxel phantoms are directly exposed to the air, which is anatomically incorrect. So therefore, we reproduce the detailed eye model adopted in ICRP publication 116 in a high quality mesh model. And we reproduce the mesh model, and then we install the model into the mesh phantom. So this is the male phantom having the detailed eye model, and this is the female phantom. And also blood in large vessels were also modeled. We modeled large vessels and large arteries and veins separately, and also their mass are exactly matched to the ICRP 89 reference value respectively. So as you can see, the mesh blood models are anatomically more realistic than the voxel model. And finally, the muscle, the large part of the muscle mesh model actually was converted from the voxel model. However, we put many effort to eliminate a considerable number of geometric defects and overlapping problem with the organs and tissues. Okay, now let's move on to part 2, the inclusion of the blood content. So the organ mass of the ICRP reference voxel phantoms are matched to the ICRP 89 reference values, which are summarized in table 2.8 in the ICRP publication 89. So when constructing the ICRP reference voxel phantom, it was generally interpreted that these reference values were assumed as inclusive of blood together with the tissue parenchyma. But finally, it turns out that the ICRP 89 reference values that I show are not inclusive of blood. So it means that the ICRP reference voxel phantoms underestimate blood inclusive organ tissue mass intended by ICRP publication 89. Actually, this issue made the ICRP adult specific observed fraction calculation a bit complicated. For example, for crossfire irradiation cases, so for example, like lung to liver, the SAF values were calculated by using the voxel phantom organ mass as a target mass, which is even not inclusive of the blood. On the other hand, for the self-irradiation cases, for example, liver to liver, the voxel phantom organ mass was not used as a target mass, but the increased organ mass, the newly calculated for the blood inclusion, was finally considered as a target mass in the SAF calculation. So as a result, two different types of the organ mass, depending on the irradiation type, were inconsistently used in the internal dose calculations. This makes a calculation process rather complicated. To overcome this issue, we decided that the mesh phantom were finally adjusted to increase the organ tissue mass for blood inclusion. So blood mass for each organ or tissue was calculated based on ICRP 89, the reference value for the regional blood volume fraction together with the total blood masses. So for example, we can easily calculate the blood mass in liver. The liver blood volume fraction is 10% for both male and female. And the total blood mass is 5.6 kilogram for male and 4.1 kilogram for female. So therefore, the blood mass in liver is 560 gram for male and 410 gram for female. In addition, the density and elemental composition for the blood inclusive organs and tissues were also calculated based on the data given in ICRP publication 89 and also the ICRU report 46, the following the equation. So the table 4.2 of the ICRP publication 145 provide the volume mass for each organ or tissue, and together with the organ mass tissue only. And also ICRP, the Annex B of the ICRP 145 provides the density and the elemental composition for each organ or tissue, which are inclusive of the blood. And this slide shows the mesh phantoms before and after the blood inclusion. So as you can see, we increased organ and tissue volumes, but at the same time, we attempted to maintain the original shape of the organ and tissues as similar as possible. So now let's move on part 3, the inclusion of the thin target and source regions. Range from 15 to 100 micrometer is the recommended as an appropriate depth for the radiosensitive, the basal cell layer. So this basal cell layer was included in the skin model of the mesh phantom. So for the inclusion, the outer skin surface was copied and then reduced by using the offset function of the RapidForm software to define the target layer within the skin model. So this is the skin model, including the 50 micrometer thick thin target layer, which are, as you can see, this thin layer is well defined in the skin model. And also the micron scales of the target and surface region of the alimentary tract system described in ICRP publication 100 were also included in the mesh phantoms. Basically, it's like the skin, we also use the offset function using the RapidForm software to model the target and source region in the all of the alimentary tract organ, only except the oral cavity. So oral cavity geometrically is complicated and therefore we need more complex procedure to define target and source regions. The food as a source region should be placed on the tongue. However, there was not enough space to define the tongue to define the food. So we divided the tongue into the two parts, upper and lower. The upper part was considered as a food only for the purpose of the SAF calculation. And then the oral mucosa in loop of the mouth is also defined. At the same time, the oral mucosa in the inner tongue is also defined in the lower part of the tongue. And in addition, the radionuclide retention region is defined by adding the 10 micrometer layer on the teeth surface, and then oral mucosa in the lips and cheek is also defined. So this slide shows the target and source regions for the oral cavity in the male phantom. And this is esophagus, 10 micrometer thick target region is well defined in the mesh phantom. And the stomach, not only 14 micrometer thick target region, but also 300 micrometer thick source region is well defined in the mesh phantom. And this is the small intestine and large intestine. And also micron scale of the target and source region of the respiratory tract system described in ICRP publication 66 were also included in the mesh phantom. Again, the same approach, using the offset function was applied for the ET1 region and also ET2 region. Meanwhile, the bronchi and bronchioles, so large BB and small BB region, actually could not be directly converted to the high quality mesh model as like a realistic tree structure of the lung airways. So we developed a realistic long airway model to represent large BB and small BB region based on airway centralized generation algorithm and also the Y-shaped mathematical model. So for the airway construction, we used the diameter and length for each branch generation given in ICRP publication 66 were used for the adult male. And for the adult female, we obtained the branch diameter and length from the scaling and interpolation method as explained in ICRP publication 66. This is the airway model of the male phantom. And for the female phantom, so as you can see, the mesh model is much more realistic than the boxer model. So in addition, this airway model can include the micron scale target and source region. Of course, the mathematical airway model we developed should be converted to the mesh format to be installed within the wrong mesh model. However, the conversion required extremely large memory allocation, which is at least at present it is impractical for the Monte Carlo simulation. So to address these issues, we used a different approach, which is that the long mesh model was overlaid with the mathematical airways directly in the Gent4 code using the parallel words function. So this overlaying approach is currently only available in Gent4, but enables those calculations to be performed for the detailed long airway model with requiring the minimal additional memory uses. And in the urinary bladder, the basal cells of the epithelium are believed to be a relevant target cell at radiogenic risk. So accordingly, the urinary bladder target layer was also included in the mesh phantom by simply using the offset function. So as a result of the development method procedure I have explained, the adult mesh type reference phantoms were born to address the limitation of the adult voxel type reference phantoms. So for the female phantom, the polygon mesh model is composed of 2.5 million triangular faces. And when we convert to the tetrahedral mesh model, we need 8.2 million tetrahedrons. The female phantom is in a similar level with the male phantom. And the Annex A and Annex B of the ICRP publication 145 provide all numerical information of the mesh phantom, such as the organ ID, organ mass, and the density, and the elemental composition, which are all needed for the Monte Carlo dose calculation. And also Annex C provides the list of the organ ID numbers to define the source region for internal dose calculation. And Annex D provides a list of the organ ID numbers to define a specific target region for the organ dose calculation. Electronic file of the mesh phantom can be freely downloaded in the ICRP website. More detailed information on the electric file will be explained by Dr. Chance Choi following my presentation later. The next, I will briefly talk about the compatibility with the Monte Carlo code. Three well-known general-purpose Monte Carlo codes, the Gent4, Pitch, and MCMP6, can handle tetrahedral mesh geometry. So we observed the runtime and memory uses for the three Monte Carlo codes under various simulation conditions. During the observation, we used the Gent4 version 10.02, Pitch version 2.92, and MCMP6 version 2.0. So overall, in runtime, Gent4 and Pitch are quite comparable. However, the MCMP6 are notably slower than other code. In memory uses, the Pitch requires about 1 gigabyte, but the Gent4 and MCMP6 required more than 10 gigabyte at the time. Nevertheless, all Monte Carlo code can be used in the personal computer, considering the maximum the memory can be equipped the 64 gigabyte. Recently, we have heard that the MCMP6 version 3 is coming soon and expected to improve the simulation performance of the unstructured mesh, including the tetrahedral mesh in general. And also, please note that the Monte Carlo example input and code file for these three Monte Carlo code are also provided in the supplemental material. Some demonstration will be shown by Dr. Choi as well later. So now I would like to talk about some dosimetry impact of the mesh phantom for some external and internal exposures. First, let's see the external exposures. So this graph shows some effective dose coefficient for the external exposure to the photon beam in AP direction, calculated from the mesh phantoms and also along with the voxel phantom. As you already know, ICRP 116 data are calculated based on voxel phantom. So as you can see, the excellent agreement between the mesh and voxel phantom, we can see over the entire energy region. Similarly, the neutron result also show the excellent agreement between mesh and the voxel phantoms, and also these support that the external dosimetry impact of the mesh phantom for both photons and neutrons will be negligibly small. So the electron cases at the energy the above 1 MeV, as you can see, the excellent agreement between mesh and boxer phantoms. On the other hand, the low energy region, there are significant difference between mesh and boxer phantoms. Even at certain energy region, the boxer phantoms underestimated the effective dose against the mesh phantoms by up to about the 10 times. So these effective dose difference are attributed mainly by the skin dose difference between the mesh and boxer phantom due to the improvement of the mesh phantom. As you already know, the skin dose of the mesh phantom were calculated by using this 15 microthit target layer, but the skin dose of the boxer phantoms were calculated by using the entire skin as our target. The helium result also showed a similar observation with the electron result. Okay, now let's see some internal exposure. This graph shows the photon specific observed fraction for some self-irradiation cases, the liver to liver, and lung to lung, and thyroid to thyroid. And these are both the male and female. So as you can see, the excellent agreement between mesh and boxer phantom can be observed for the most of cases. And also the electron specific observed fraction for self-irradiation cases also show similar observation with the photon SAF values. So these results support that the internal dosimetry impact of the mesh phantom for both photon and electron self-irradiation cases will be negligibly small. But this graph shows the photon specific observed fraction for crossfire irradiation. This is the lung to red bone marrow, and this is the lung to spleen, and this is the liver, lung to liver for the male and female. So overall, as you can see, generally good agreement between mesh and boxer phantom, except for very low energy region below 20 keV only. But on the other hand, for electron specific observed fraction, the difference between the mesh and boxer are significant in general. And especially the notably large difference can be observed when red bone marrow is our target. This is due mainly to the improvement of the skeletal system in the mesh phantom. As explained before in the boxer model, the spongiosa, including red bone marrow, is not fully enclosed by the thin cortical bone due to the limited boxer resolutions. And the rib spongiosa is even in contact with the lungs. So that's why the electron specific fraction of the boxer phantoms are significantly larger than the boxer phantom result. So this is my last slide. Due to the limited time, I think all the details on the adult mesh style reference phantom could not be covered in the presentation today. So in addition to the ICRP publication 145, here I also listed key references which should be informative to be checked for learning more about adult mesh type reference phantoms. Thank you for your attention.
Okay, thank you. Just let me to check. Okay, thank you for the nice presentation, Yeonsu. It was a great talk. Now we'll move on to the next presentation. And the title of next presentation is how to download and use phantoms. This presentation will be given by Dr. Chan-Soo Choi. Dr. Choi is currently working as a postdoctoral researcher at University of Florida on computational human phantoms. He is also serving ICRP as a member of Task Group 103, which is developing mesh-type reference computational phantoms. Dr. Choi received his PhD degree in nuclear engineering at Hanyang University in Seoul, Korea in 2022. That is last year. Dr. Choi also worked on mesh-type reference computational phantoms. During his PhD study at Hanyang University, he helped Professor Yeon Soo-yeon to develop adult mesh-type reference computational phantoms. Then he himself developed pediatric mesh-type reference computational phantoms as the main developer. Dr. Choi is also very active in research. Even though he got his PhD degree just last year, he already published 39 journal papers and made more than 100 presentations at technical conferences. Okay, with that, I think we can start. Chan-Soo, if you're ready, please go ahead.
Thank you very much for kindly introducing me. I'm Chan-Soo Choi from the University of Florida, and I'm also a member of Task Group 103. In this presentation, I'm going to explain how to download and use the ICRP 145 adult mesh phantoms. As Dr. Yum already said, the ICRP is currently providing the electronic files with the publication 145. So those who want to use the phantoms can download the electronic files by clicking the What to Do, Publications, and ICRP Publication 145 on the website, and then clicking the supplementary material here. Through this presentation, I'd like to explain these electronic files as much detail as possible within the given time, and also provide some practical information about using the phantoms. The downloaded files are composed of two large folders. One is the phantom data folder, and the other is for the Monte Carlo codes examples. And first, I'm going to explain the phantom data folder. The phantom data folder is composed of MRSP-AF, adult female, and MRSP-AM, adult male folders, and each folder has 8 files with element, node, object, material library, media, bone, blood, and PDF file formats. Among these phantom data files, the node and element files are for the tetrahedral mesh phantoms. As mentioned in the previous presentations, the ICRP 145 phantoms developed for the Monte Carlo dose calculations are the tetrahedral mesh phantoms composed of millions of tetrahedrons. So I think it'll be helpful for the users to understand the structure of these files for the Monte Carlo dose calculations. The node file contains the point data making up the tetrahedrons. In the first line of the node file, the number of nodes and dimension are listed sequentially. The remaining lines are the data for each point. In these lines, the node ID and its X, Y, and Z coordinates are listed. With this node data, the element file constructs a tetrahedral mesh. In the first line of the element file, the number of tetrahedrons, nodes per tetrahedron, and the number of attributes are listed. Here, 1 is written as the number of attributes because each tetrahedron contains only one attribute information, the organ ID. The remaining lines are the data for each tetrahedron. In these lines, the tetrahedron ID, four node IDs making up each tetrahedron, and the organ ID assigned to each tetrahedron are listed. Next are the object and material library files, which are for the polygonal mesh phantoms. Even if the ICRP 145 phantoms are the tetrahedral mesh phantoms, the ICRP is providing the polygonal mesh phantoms as well for the users interested in the modifying the phantoms, because they are compatible with many commercial 3D CAD programs such as 3ds Max, Rhinoceros, and Blender, thus making it easy to modify. Of course, these files can be used in some Monte Carlo codes such as GM4, but as Dr. Young said, they are not recommended because of the low computational speed and compatibility with other Monte Carlo codes. The objective file contains both the vertex and face data for polygons, and the material library files just contain the color information. In general cases, the users do not need to read or modify these files directly, so I will omit the detailed explanation on the structure for the sake of time. After the modification using the 3D CAD programs and the like, the users can easily tetrahedralize the phantoms using the poly2tet program based on the Tetogen program, and then use them for the Monte Carlo dose calculations. Please refer to the poly2tet paper for the detailed process for the tetrahedralization. Next is the media file, which is a copy of table in Annex B. The media file contains the physical property information, such as elemental compositions and densities for each tissue. The elemental compositions were expressed as the percentage by mass, with the summation of 100%. The users should keep in mind that the medium number are not the same as the organ ID. The medium numbers represent the tissues with the same physical properties, while the organ IDs are further subdivided according to their use or location, even though they have the same physical properties. The information on the medium number corresponding to each organ ID is listed in the table in Annex A. So the users can refer to this table to use the phantom by matching the IDs like this. Next is the blood file. As Dr. Young said, the organs of ICRP 145 phantoms contains the blood content, and this file provides the information on the fraction of the blood content in each medium. For example, the medium number 1 and ratio 0.159 indicate that 15.9% of blood content is contained in the tissue with the medium number 1, and the rest are the same way. This file can be used in the cases where the blood is considered as source regions and the like. And next is the bone file. The cortical bone and medullary cavity are composed only of the cortical bone and yellow bone marrow respectively, but the spondiosa is a complex mixture of various skeletal tissues such as red bone marrow, trabecular bone, yellow bone marrow, and miscellaneous tissues. This file contains the information on the fraction of skeletal tissues in each bone site. The blood content was distributed to each skeletal tissue in a different fraction, so we provide a ratio for both inclusive and exclusive of blood content. For example, the red bone marrow contains a large amount of blood content compared to other skeletal tissues, so we can see each ratio increases for inclusive of blood content. This file can be used for the bone dosimetry or when some skeletal tissues are source regions. And I will explain more details about the bone dosimetry at the end of this presentation. The last file in the PDF, is the PDF file. Using this file, the users can visualize the phantoms in Acrobat without using the 3D CAD programs. The users can easily rotate the phantoms, move the phantoms, and enlarge or shrink the phantoms, and turn on or turn off the organs, and change the lighting, and also look at the cross-sectional views like this. In addition to these functions, the Adobe website provides more information on the functions. Next, I'm going to explain the folder for the Monte Carlo code input examples. The current distributed electronic files do not have the long array folder shown at the bottom, but we're gonna update this folder soon. So I will briefly deal with this folder as well in this presentation. There are 3 Monte Carlo codes, Fitch, MCMP, and GM4 that need to covered in this presentation, but time is very limited. So I will try to deliver at least enough information for the users to run the code. Of course, we need to understand or study each code to modify the input examples for each calculation purpose. Each Monte Carlo code folder contains the external, internal, and phantoms folder. The external and internal folders contain the input examples for external and internal exposures respectively, and the input examples are almost identical except for the source definition part. The phantoms folder contains the phantoms and relative numerical data required for the Monte Carlo dose calculation. This slide shows the external and internal exposure scenarios assumed in the input examples. For both exposures, the particles were assumed to be isotropically generated 1 megaelectron-volt photons. And for external exposure, the particles were assumed to be generated 1 meter in front of the phantoms. And for internal exposures, they were assumed to be generated in the liver. For both exposures, the mean observed doses for each organ ID is output as result. And first, I will explain the input examples of Fitch code. As I mentioned before, the input examples for both exposures are almost identical except for the source definition part. So I will explain with the input example included in external folder. And this and following slides show the entire input example of Fitch code. This file consists of 6 sections: parameters, source, material, surface, cell, and T-deposit sections. In the parameters section, we can set various parameters of Fitch. The parts the users need to pay special attention are file 7 and file 20 parameters. The user should enter the path of nuclear data named XSDIR in the file 7 parameter and path of EGS folder in the file 20 parameter. They are included in each user's Fitch installation folder, so it depends on each user's environment setting. We can also set the number of particles, output file name, and physics and the like in this section. But for this, you can refer to the Fitch manual for more detailed information. The path setting has become easier in the Fitch version 3.0 and the later versions. The users can delete the file 7 and file 20 parameters and just add file 1 parameter with the Fitch installation folder path. Then the aforementioned paths are automatically set. In the surface section, we can set the surfaces to be used later in the cell section. In the surface section, 3 surfaces are defined. The first surface is the phantom box with surface number 10, which includes the phantom. And the second surface is the box with the surface number 20 for the universe and field, which should be slightly larger than the phantom box so that we can fully fill the phantom box with the tetrahedral mesh phantom. The last surface is box defining the world, which with the surface number 99, which is the boundary where the particles are no longer transported. Using these surfaces, the cells are defined in the cell section. There are many contents need to be entered in the cell section. So the cell file was written separately in the phantom folder, and this is read in the input example. In the cell section, we first have to make the cell for the universe by using the aforementioned box with the surface number 20, which is slightly larger than the phantom box. By setting the lattice parameter 3 to 3 and T file with the phantom path, and this cell is filled with the tetrahedral mesh phantom. Then we have to make the cell by using the phantom box with the surface number 10 and implement the tetrahedral mesh phantom by using the fill function. For your reference, the number for the universe and field should be same. And in this example, the universe and field number was set to 15,000. Then this universe should be filled with each organ and tissue. The process for setting the organs and tissues are the same as the general fit cell process. We have to set the cell number, material number, density, surface, and universe number. And to avoid the confusion, we set the universe number, cell numbers, and material numbers all equal to the organ ID in the input example. The following is the material section. As in the cell section, there are many contents need to be entered in the material section. So the material file was written separately according to the Fitch material format in the phantoms folder. Here, the physics properties corresponding to each organ ID are already matched, unlike the media file described before. And in the T deposit section, we can calculate the energy deposition of the organs. The mesh parameter is set to the reg, which means that the tally will be installed using the cell numbers, that is the organ IDs. As mentioned before, the mean observed doses for each organ ID is output as results, so the reg parameter is set to all. If the users want to calculate the result for the specific organ, the corresponding cell number should be entered in the leg parameter. And if the users want to calculate the result for several organs together, their cell numbers should be entered in the parentheses. The following is the source section for external exposure. As far as we know, there is no point source in the S-type parameter defining the source shape. So the point source was defined by setting the S-type parameter to 1, which means the cylindrical source, and then setting its radius and height to 0. For internal exposure, the source regions are defined using the rejection method. For this, the box-shaped sources surrounding the liver are first defined, and after that, the cell number of the liver is entered to the reg parameter so that only the sources included in the liver are transported. The source setting for the internal exposure has become easier in the Fitch version 3.02 and later versions. The users just need to set the S-type parameter to 24, which means the tetrahedral mesh source, and then enter the cell number of the liver to the tetrag parameter. This concludes the explanation on the Fitch input example, and I just want to give you one tip to reduce the implementation time. If the tetrahedral mesh phantoms are very complex, the implementation time of input file can take very long time. So if the users want to perform multiple simulations with the same phantoms, there is a method to significantly reduce the implementation time. Although I didn't explain it in detail before, there is a parameter named itetra in the parameter section. The itetra parameter is currently set to 0, which means the input example reads the tetrahedral mesh model in the element and node format. What the users need to do is just change the itetra parameter to 2 and run the input file. Then even if the source particles are not transported, something looks like the simulation is performed immediately to create the tetrahedral mesh model in binary format. After that, the users can use the created binary file to run the simulation by changing the itetra parameter to 1 and run again. Even if this initial task may be a little cumbersome, it can significantly reduce the implementation time from 15 to 1 minute when performing multiple simulations. And here's a demo video of executing the input example in Fitch code. To show the users how to apply the foregoing, I didn't run the file right away, but modified the file a little bit. First, I opened the input example and deleted the file 7 and file 20 parameters and add the file 1 parameter. Also, I can't stop the video. So delete the file 7 and 20 parameters and add the file 1 parameter and change the itetra to 2. Then I executed the input file. And here we can see the binary file named tetrabin was created. Then I can change the itetra parameter to 1 to read the binary file. And after that, I again executed the file. And we can see the simulation runs well. And also we can confirm that the dose for each organ is well calculated. Next, I will explain the input examples of MCMP6 code. Like the Fitch code examples, I will explain with the input file in the example external folder. And this and following slide shows the entire input example of MCMP6 code. As you may already know, the MCMP input file is written in the order of cell card, surface card, and data card, and all the cards except for the surface and cell cards are included in the data card. In the surface card, we can set the surfaces to be used later in the cell card. In this card, 2 surfaces are defined. The first surface is the phantom box, which encloses the phantoms, and the second surface is the box defining the world, which is the boundary where the particle no longer transported. Using these surfaces, the cells are defined in the cell card. There are many contents need to be entered in the cell card as well. So the cell file was the cell file for the pseudocell, which are the cells for the organs and tissues, was written separately in the phantoms folder. The process for setting the organs and tissues are the same as the general MCMP cell process. Here, we have to set the cell number, material number, density, surface, and universe number. And for the pseudocell, the number for the surface part should be 0. And the universe number for all organs and tissues should be the same. Same number, and in this example, the universe number is set to 2. Please note that cell for the background should be defined as the extra pseudocell, which is the non-tetrahedral mesh phantom part inside the phantom box. Then the cell for the phantom box and word is defined in the input files. We have to fill the phantom box using the field card by setting the same number used in defining the pseudocells, that is 2. The tetrahedral mesh phantoms can be read by using the embed card, which should be written in the data card. The MCMP supports the tetrahedral mesh geometry in Abacus file format, not in element and node file format. So the phantoms in Abacus file format were generated and already included in the phantoms folder. For your reference, the Abacus file can be generated by using the element and node files using the TET2MCMP program. Coming back to the embed card, the number behind the embed card should be the same as the universe number of the phantom. And in this example, this is 2. Then we have to set the geometric type and phantom file path by using the mesh geo and mgeo in card. We also have to set the background by using the pseudocell of the background defined in the cell card. And finally, we have to set the material for the pseudocell using the mesh card. The mesh card should be defined with the integer pairs for each pseudocell. The first number is the embedded pseudocell number, and this number must be sequential starting at 1. And the second number is the pseudocell number, in this example, the organ ID. The following is the material card. As in the cell card, there are many contents need to be entered in the material card. So the material file was written separately according to the MCMP material format in the phantoms folder. Next is the tally card. We can calculate the energy partition of the organs using the place F6 tally. To create a tally for each organ ID, they should be written individually. So the tallies were written separately in the phantoms folder. If you want to calculate the result for the several organs together, their cell numbers should be entered in the parentheses. The following is the source card for external exposure. And unlike the pitch code, the point source is simply defined by setting the source position to 0, -100, and 0 in the SDF card. And for the internal exposure, unlike the external exposure, generating the sources in the liver is a bit more difficult because in addition to the input example, the Abacus file also should be modified. For this, the source position should be set to the volumer in the input example, and then the set source lines should be added in the Abacus file. And for your reference, the number in the middle means the number of tetrahedrons of the source organs. If the users want to set multiple organs as source regions, these lines should be added for each organ after only changing the number of tetrahedrons and organ ID. In the case of MCMP code, the implementation time of input file takes much longer when compared to pitch code. So the users can significantly reduce the implementation time using the UMconvert program which is already installed during the installation process of MCP 6.2 version. And for this, the users should enter the convert command in the command window, and also enter the Abacus file name and MCP out file name using the options on the right. For your reference, the conversion process can take about half a day. And then in the embed card, the users should set the MGO and MeshGeo and MGO in card. The Abacus should be changed to the MCP and the Abacus file name should be changed to the file name. And although it takes a long time to convert once, the implementation time is reduced from about half a day to 2 minutes. So using the file is very helpful when performing the several multi-color simulations with the same phantoms. And please note that the MCP file should be regenerated every time if you want to modify the Abacus file to set the different internal organ sources. Here's the demo video of executing the input example in the MCP code. I'd like to show you how to run the input example after modifying the input file, which reads the Abacus file to read the file. Creating the file takes very long time, so I already created the file in advance. And I open the input example. And then set the MeshGeo to file, MeshGeo to MCP and also set the MGO in to file, as I mentioned right before. Then I executed the input example. And after that, through the output file, we can confirm that the mean observed dose for each organ is well calculated in the output file. And next, I will explain the input example of GM4 code. Unlike the other multicolor codes, the GM4 input examples written in C++ consist of many headers and source files. And as you may know, the GM4 provides the users with a high degree of freedom, but there is a high barrier to entry. It is virtually impossible to explain all the header and source files in detail within the given time. So I'm gonna only give very brief overview of the entire file structure and how to run them. This slide shows the classes making up the geometries of the input example. TET detector construction class constructs all the geometries, including the phantom box, and world. For this, the phantom data are read in the TET model import class, parameterized in the TET parameterization class, and then transferred to the TET detector construction class. And this slide shows the classes for organ dose calculation. TET detector construction class not only constructs geometries, but also creates the score to get the doses in the organs. The energy position for each organs and tissues are calculated and collected by using the TET PS energy deposit and TET run classes. Then the doses are printed through the TET run action class. In addition, the classes performing various functions are included in the input examples. The sources are generated in TET primary generator action class. For external exposure, a G4 general particle source class is used. So only the basic information for configuring this class are included, and the most source information are specified in the separate source definition file named source mec. So if the users want to modify the source information, we can do most of that in the source definition file. On the other hand, for the internal exposure, default particle guns class is used to change the source position for each event. So the particle type and primary energy information specified in the source definition file and source regions can be set through the comment line. The detailed information will be explained later. This slide shows the source definition file. As I said right before, for external exposure, the particle direction, energy, type, geometry, and position can be set through the source definition file. And for the internal exposure, only the particle type and energy can be set. The path of the source definition file is set in the input macro file, which makes various settings for executing the simulation. In this file, the users also can set the number of threads and the number of primary source particles. In this slide, I'm going to explain the process for compiling the GM4 input examples. First, we can go to the folder containing the examples, such as external or internal folder, and create a new folder for the build. And here, this folder name is example build. Next, we can go into the new folder and do the cmake and do the make for the compile. If the compiling process is successfully done, you can see that the executable file as named of external or internal are created. With the created executable file, we can perform the Monte Carlo dose calculations. And for this, first, the name of the executable file should be written after the /, and the names for the input macro and output file names should be written using the -n and -o options. And actually, the male phantom is read by default, and the female phantom can be read by adding -f option. And for internal exposure, the source regions can be set by typing the list of the organ IDs just behind the -i option. And here's the demo video of executing the input examples in GM4 code. Through this video, I'd like to mainly show the compiling and executing process. As I mentioned right before, I created a new folder named example build and went into the folder and did a make, and after that, did a make, thereby creating the executable file. And then I opened the input macro file and changed its executing setting, such as number of threads. Next, I ran the executable file with the options described right before. And we can confirm that the dose for each organ is well calculated in the output file. The last input examples are about the lung arrays. As I said before, this folder is not included in the current electronic files, but we're going to update this folder soon. So I will briefly explain this folder. As Dr. Young said, the lung arrays were constructed in the CSG format based on the numerical data, not in the tetrahedral mesh format because of the memory issue. So they can be implemented only in the GM4 code, which has the high degree of user freedom, and thus most of the file structure is the same as the GM4 input examples described right before. The difference is in the phantoms folder. each airway generations, location, diameter, and volume informations were added. The long airways in the CSG format are overlaid on the tetrahedral mesh phantom using the G4V user parallel word class. As I said before, most of the file structure is the same as the GM4 input examples, so the compiling and executing process is the same. After we run these files, the long array information are output along with the phantom information, and we can get the mean observed dose for target regions of long arrays, such as large BB and small BBs. For internal exposure, the very thin source regions of the long arrays cannot be defined by the same method as the liver source, because the long arrays are not in the same format. So we extracted the source position information using the rejection method in advance and added them in the new folder named source. So what the users need to do for using these source regions is enter the -i option as before and enter the source region accruement listed on the slide, not the organ ID. After we run these examples, the long array information are again output along with the phantom information, and we can get the mean observed dose for long array target regions. This concludes the explanation of all the electronic files. All folders contain the README files, including the detailed explanation, so I believe they will also be of great help to the users. And additionally, I'd like to give you one tip regarding the skeletal dosimetry. Like the ICRP 110 voxel phantoms, in the ICRP 145 mesh phantoms, the skeletal target tissues, that is active marrow and bone endosteum, are macroscopically defined as the spondiosa and medullary cavity. So these tissues are usually replaced by those to spondiosa and medullary cavity, assuming these tissues are homogeneously distributed in the spondiosa and medullary cavity. More specifically, if the users want to calculate the dose to active marrow, first, we have to calculate the spondiosa dose for each bone site, and then multiply it by the ratio of active marrow included in each bone site to total active marrow. Then by adding all of these, we can get the dose to entire active marrow. The method for the bone endosteum is similar, but unlike the active marrow, the bone endosteum is also included in the medullary cavity, so we can see that there is one more term. The ratio data of the active marrow and bone endosteum for each bone site can be found in the table 4.2 of publication 110. For photon and neutron exposure, the users can use the more advanced method named full-on to dose response functions. In the method described right before, the dose to spondiosa and medullary cavity replace the dose to skeletal tissues contained therein. But for this method, we need to calculate the full-ons for each spondiosa and medullary cavity first, and then multiply the full-ons to dose response functions corresponding to incident energies. And after adding them, we can get the dose to the skeletal tissues for each bone site. And finally, we can get the dose to entire skeletal tissues after applying the ratio data and adding them in the same way as previous method. The full-ons to dose response functions were generated based on the micro-city images, and they are listed in annexes D and E in publication 116. The current input examples have the tally calculating the energy position, but for using the plus those response functions, the full length should be calculated. So in the feature code, the t-track parameter should be used instead of the t-depart parameter. And in the MCMP code, F4 tally should be used instead of the plus F6 tally. Also, to multiply the plus those response functions corresponding to instant energies, in the feature code, the multiplier section should be used. And in the MCMP code, DDF cards should be used. And for the GM4, all these modifications can be made in the G4 primitive scorer class. It can be difficult to use these methods at the first time, so we also provide the input examples for the plus those response functions on the Mesh Phantom website, and I think it'll be very helpful. And finally, I would like to introduce the Mesh Phantom website. The Mesh Phantom website not only provides the Mesh Phantoms other than the ICRP 145 Phantoms, but also provides more diverse versions of input examples as mentioned before. Also, if the users post any problems regarding the Mesh Phantoms on the forum, we will try to provide the solution or find some solution together. And that's all for my presentation. And thank you very much for listening until the end.
Okay, thank you. Thank you so much, Chansu. It was a great talk. I think you provide very useful information from a practical point of view. I think we'll start Q&A time. But there were a lot of questions, actually. There are more than 20 questions, and we already answered those questions. So I think if you have questions, like you can write your question in the Q&A window. I think is the way to go. Or I don't know if you can raise your hand, and you can use a microphone. But so I think the speakers can review the questions, picture already answered, and probably you can, if there's anything you can add, if you want to add, I think we can add now. Mostly they are, I think, well answered, but if you want, you can add more comment. There is one question. I think this is for so max agreement means within what percentage? This question is not really clear, so we were not able to answer this question. But so do you think you can answer this question?
Actually, I don't exactly understand what is the exactly meaning of the max. Is it those coefficient between voxel and mesh, or so?
I don't know. So probably I don't know. So at this point, we will skip this question, and now we have only one more question, I think. That is, I'll read the question. Hello, will effective dose be the metric for measuring stochastic risk for the phantoms, or are there other quantities being considered? It is about effective dose. I think I don't think we can answer this question at this point. Measures stochastic risk. Yeah, this is for stochastic risk. There are any other quantities being considered? No, I don't think. If there's anyone who can answer this question, please you can turn on your microphone, and I think we can answer. We are not the one who can answer this question at this point, I think. Yeonsu, I think you don't have to write you can answer this question
Okay.
using your microphone.
Sure. So I think there are multiple questions there.
Mhm.
Okay. So max agreement actually very high energy. At the high energy 10 to the agreement is good. So it's less than like 0.1%. They're good agreement, but yeah, so that will be answer. So essentially there's no significant difference for the photon and neutron cases. And as I explained, yeah.
Yeah, I think it's within statistical uncertainty.
Right.
Okay, there's one more question for source terms. Are you only allowed to input monoenergetic particles? Any chance to use energy emission spectrum of particles, such as beta particles? Anyone want to answer this question?
Okay.
Okay, Ramo.
I think you're asking about the supplementary files, the MC code examples, but I think we are just providing some simple case for the calculation for external and internal cases. So you can just modify the JAN4 code or MCMP or fetch input files to generate particles with energy spectrums.
Yeah, you're right. Our source is very simple. Then you can modify the source to make your own source geometry. Okay, there's one more question. What is the possibility of introducing a dynamic source distribution within the phantom body? A dynamic source distribution? So it's a moving source, you mean? It's possible to introduce a dynamic source distribution. We never thought about this one. I don't think we have any plan for this. It's too much. It is about a biokinetic model. We are developing computational phantoms, and is combined with biokinetic models to calculate organ dose and effective dose eventually. So. So if there are any questions, you can ask now. We still have time.
So
Yeonsu?
So he also gave some word on radio
Radiopharmaceutical dosimetry.
Yes. So nuclear medicine dosimetry, right?
Yes, I think this question is connected to the previous question. How can I get there's a new question. How can I get the CT image of phantom? I think you can simulate a CT, and some people already is doing this one. So someone just can explain how.
So is it CT image of the reference phantom, or
it looks like? I think you can just simulate the X-ray or the CT anyway.
Maybe I think if the questioner needs the original CT images of the phantom, maybe we cannot answer. It could be possible or not.
So we don't have.
Yeah. Actually, you have to ask the Helmholtz the research.
Maria Santo. So yeah, you don't have the original CT image to produce ICRP 110 phantoms and mesh type reference computational phantoms. I think you need to contact Dr. Maria Janko in Germany. Yeonsu and Chansu and Bango, if you have anything you want to say for the answered questions, and you can do. But we have, I think, more.
I think for the entry-level user, we recommend the Fitch or MCMPUs because for the GM4 code, we have to very well know about the C++, so it is very difficult to use for the entry level. But for the Fitch and XMP code, the entry level user can write the simple input file only using the manual.
Right. GM4 code itself is very difficult to use, so I think if it's entry level, I think you can recommend the Fitch or MCIP. Okay. I think it's not English, right? I don't think it's English. Okay, I think you just ignore it. You can ask question in English.
No question more.
I think we're done. Looks like there are no more questions, so probably we can close now.
Okay, so in chatting box, the Charlotte mentioned that maybe the webinar and the recording of this webinar and slide will be available on the
Yes,
ICRP
we'll provide the slides in PDF file. So it'll be posted, so you can download the slides. And also ICRP is recording this webinar, so it'll be also uploaded, so you can watch whenever you want. Okay, I think that's it. We'll close now. Thank you for attending this webinar. I hope it was helpful for all of you in understanding and using the mesh type reference computational phantoms. And if you have any questions after this webinar, then please send email to us. Then we'll try to answer your questions, and I think it'll work. It is also my understanding that the webinar was recorded and will be posted on the ICRP website, just I mentioned, so that you can watch it whenever you want in the future. Okay, with that, I think we'll close this webinar session. Once again, thank you for attending this webinar. Thank you. Thank you so much.